Hi, I'm Yurong, and I will be presenting our work, HiSci 2020, Leveraging Path Traversals to Aid 3D Perception. 3D perception is a crucial problem for autonomous cars. Specifically, it needs to read sensor data like 3D LiDAR scans and figure out the positions of other traffic participants to plan its route. Though there has been significant advance recently, it is still challenging to disambiguate objects, especially when they are small, highly occluded, or far away. Most approaches view this problem simply as an instance of supervised learning. While trained data come with labels, and during test time, the model should rely only on instantaneous data for inference. However, is it the best way to model the problem? A reality of driving that was previously ignored is that people tend to drive on the same route they have driven before. You drive to school, to work, to shopping, and even if you embark on a new route, it is highly likely that you are following the footsteps of other drivers. This is a distinct opportunity. Path traversals, of course unlabeled, at the same location is available to the car, even at test time. Can we possibly exploit such nature to enhance 3D perception and even allow them to continue improving after deployment? We start with two practical observations about the data. First, we know that with current technology, accurate localization can be easily obtained along with LiDAR data. This allows us to align the point clouds both within one traversal and between traversals. Second, as people will drive through the same route over and over, for each LiDAR scan, we can get multiple path scans of the same location, even at test time. This is distinct from vanilla 3D perception, which basically treats each LiDAR scan as completely new. These assumptions are very practical and add almost zero additional cost for real-world application. The system only needs to save LiDARs and the corresponding localizations for future reference. So, how can these unlabeled path traversals help? First, by simply checking if there are points persistently present across traversals, we can easily tell whether a point belongs to background or not. Moreover, if we can somehow encode environment semantics from path traversals, we may exploit the prior from it. For instance, cars tend to drive within lanes, and pedestrians tend to be on sidewalks. To implement these intuitions, we propose the following. To start, T different path traversals of the route of interest are aggregated into T dense point clouds, as shown on the right. We then capture the environment semantics by processing each of them separately with a featurizer and obtaining spatially quantized features. We then apply a voxel-wise aggregation function to reduce these features into one sparse tensor for later reference. We denote it as squash features. The squash feature can be thought as a historical reference for the current LiDAR scan. To relay the history, for each point XYZ in the current scan, we retrieve the features within a neighborhood of the point in the squash and compute a weighted sum with learnable weights. In practice, such an operation can be efficiently implemented by a 3D filter on the squash feature. Such a design makes it compatible with most LiDAR-based object detection models, as long as they can take point clouds and per-point features as input, which is very common. We dub the whole framework as HiSci, which computes the squash from path traversals and then endows the current scan with features queried from squash. One of the highlights is that the whole model, including the featurizer for the squash, can be trained end-to-end with the same labels used to train a vanilla 3D object detector. The squash features comes with no additional cost. The squash can be processed and stored offline, and during inference, it can be directly loaded to make highly accurate and path-aware detections. The query operation is extremely fast and guarantees low latency. The squash features can be updated once new traversals are collected. We conduct extensive evaluations and observe consistent and significant performance boosts on almost all detection models, datasets, distance ranges, and object types we test. We also qualitatively observe the GANs from HiSci, where it outputs much fewer false positives while being able to detect the true objects exhaustively. In conclusion, the HiSci framework utilizes path traversals which are previously ignored to significantly improve 3D perception. Our method is general, easily trainable, and introduces very low latency for consistent performance scans. Please read our paper for more details. Thanks for listening.